All right, guys, good morning, good afternoon, good evening. Welcome to the video. We are going to try doing some videos like this for the next couple weeks while we are social distancing and trying to make sure that we're keeping track of what we need to do so that you guys are on par with what you need to know for pre-calculus and going forward. So what's the topic that we're going to talk about when we go to the videos? At least the first one is going to be exponentials and logarithms as inverses. Now, we've talked about exponentials quite a bit. That's the last chapter that we were on. We've also mentioned inverses before back in the first semester. So now it would be nice to know, how do exponentials and logarithms behave as inverses? So what are the learning targets for today? The learning targets for today, can you graph exponentials and logarithmic functions? Now, we've graphed a lot of exponentials before, both on paper and with the calculator. Can we graph logarithmic functions, both on paper and with the calculator as well? Can you state the inverse of an exponential or a logarithmic function? That would be something else that we'd be interested in. So right off the bat, the first thing we have is a little vocab. Well, the vocab that we hopefully know is what is a function inverse. A function inverse is a function that reverses or undoes another function. So we've seen that the square root function undoes the squaring function. For quadratics, we know that squaring functions undo square roots. We know that cubes undo cube roots. We know lots of different inverses. It'd be interesting to see how do exponentials and logarithms behave as inverses. So the first thing we have you do is kind of like a warm-up, kind of a precursor, is can I find the inverse of these two algebraic functions? Since you watched the video that I posted on Canvas, hopefully you did. If you didn't, you should go watch that video first. Can you find me the inverses of these two functions right here? So I will ask you to pause the video here in a second and actually take some time to try to find the inverses. So can you find the inverse of the first function? The first function is negative 2x cubed plus 1. And then the second function is negative x minus 5 over 3, which is the same thing as negative 1/3 x minus 5/3. How did I get that? Well, the negative is like a negative 1x. If you take negative 1 divided by 3, you'll have negative 1/3 x. If you take negative 5 divided by 3, you'll have negative 5/3. So right now, can you pause the video and can you find me the inverses of these two functions? All right, hopefully that wasn't too bad. So right off the bat, I will kind of move my paper down so that you can see kind of what the work looks like for the inverses, and we'll talk about it real fast. So let's start with negative 2x cubed plus 1. First step for finding an inverse, switch x and y. So notice right away, I know that f of x is the same thing as y. So our flip-flop the x's and the y's. Now you just have to solve for y. So if I have x equals negative 2y cubed plus 1, I'll subtract 1 from both sides. I'll divide both sides by negative 2. Then I'll be left with y cubed is equal to x minus 1 over negative 2. How can I get rid of a cube? I can use a cube root. Remember, a cube root is the same thing as a 1/3 power. And then I'm going to work up here. Now I have y by itself, which is the cube root of x minus 1 over negative 2. Since I have y by itself, that would be the inverse. Remember, we do have special notation for an inverse. That special notation for an inverse would look something like this. After negative 1 of x is the inverse, and the inverse is this cube root of x minus 1 over negative 2. Now how about the other one? If I flip-flop x's and y's, I get something like x equals negative y minus 5 over 3. I'll multiply both sides by 3. If I do that on this side, so multiplying by 3 will cancel this 3 down here. If I multiply this side by 3, I get 3x is equal to negative y minus 5. I'll add 5 to both sides, which will give me negative y on this side by itself is equal to 3x plus 5. Divide both sides by negative 1, and y is equal to negative 3x minus 5. So the inverse is negative 3x minus 5. Now, these two functions that we started with here and here are actually not too bad to graph. What I did is I actually made a small table. So let's say that I didn't know exactly what that looks like. I know from parent functions that if I have a cube, it's going to be a snake graph. Here I have a highest power of x, which is 1, so I know it's going to be linear or just a straight line. But I make a little table. So what I did for this cubic is I chose negative 1, I chose 0, and I chose 1. I plugged them into the function, and I got back 3, 1, and negative 1. So when I graphed those points, it helped me kind of shape out what the snake graph was going to look like. I got something like this. And then for the linear function, we know we don't necessarily need a table, but it might be helpful later on for inverses of exponentials and logarithms. So I just graphed straight up negative 1/3 x minus 5/3. That's Alexa in the background. That's funny how that goes. So I just graphed this right away. Alexa, turn off. So the y-intercept is negative 5/3. You're going down 1 over 3. So I start at negative 5/3, which is almost negative 2. I went down 1 and then over 3. And then I graphed my line, I got something like this. Now the nice thing about inverses, we said that the first step for finding an inverse was just flip-flopping the x's and the y's, which is kind of nice. So that means if I wanted to find the inverse of negative 2x cubed plus 1, and since I have it here algebraically, I can just flip-flop the x's and the y's when I'm graphing to help me graph it. So then if I take my little table here that I've created, this negative 1, 3, 0, 1, 1, negative 1 to help me graph this function, I can just flip-flop the x's and the y's. So instead of negative 1, 3, I would graph 3 and then negative 1. Instead of 0, 1, I would graph 1, 0. And then instead of 1, negative 1, I would go negative 1, 1. So the graph would look something like this. So then if I have a hard time seeing what that looks like in terms of a cubic, I can graph it. So I have some things preloaded on my calculator. So all the little functions I'm going to be needing here. So since this is x minus 1 over negative 2, I can turn that one on, so at least I can show you what the graph would look like. So then if you graph it, you see the graph would look something like this. So at the very least, you could see what it looks like. So then if I go back to my paper, I can use that as kind of a preliminary sketch, and I can work to make it work right. So we'll go here, and it will go downwards and out this way. So then if you sketch it in a little darker, you'd see something like this. All right. And the nice thing graphically about this is that the two graphs are symmetrical. They're symmetrical over the line y equals x. Why is it symmetrical over the line y equals x? Because the first step in finding an inverse is flip-flopping the x's and the y's, which means that the y's are equal to x's and the x's are equal to y's. So at the very least, we can see the two sketches like here. If I want a better version of this, because I'm not always the best at drawing, I can go back to my graphing calculator. I can turn on the original function that we had. I can graph that here as well. And you can see something like this. And then if you graph the line y equals x, you'll actually see that the blue line, if you flip it over the line y equals x, will be the red line, and vice versa. So I can do this again. You can also use the table feature on the calculator if you have that. If not, you can download a free version of the calculator onto your computer or your Chromebook at home. So here are some values from the table that I could take. And then notice if I go back to my other graph, so let's say I go back to the inverse, and I go to that table, you'll see that the x's and y's are just flip-flopped, which is kind of interesting. Okay, so then how about the other graph? Well, we have this linear function here. That was the original that we had. We do know that its inverse is also a linear function, so that's not hard to graph. We can go down to negative 5. That's going to be the y-intercept. And the slope is negative 3, so normally I would go down 3 and then over 1. But then going down 3 and right 1 is equivalent to going up 1, 2, 3, and left 1. I could do it again, go up 1, 2, 3, and left 1. I get something like this. And then if I sketch it in, I'll have this guy. And here. And the nice thing about these inverses, just like the first two that we had on the left sides, notice they are kind of symmetrical. They're symmetrical over the line y equals x. So then if I took this original one and flipped it over the line y equals x, I would get the one in purple, and vice versa. And you could do the same thing on the calculator if you want to see it. It's not terribly hard to do. So really quick, I can turn on those two graphs for you really fast. At least that way you can see a nice version of the graph if my hand depictions aren't good enough. And there you have it. So kind of interesting. This idea of using the table and then just flip-flopping the x and y coordinates is going to be the helpful hint as to how to find inverses for exponentials and logarithmics. So without further ado, on the bottom of your page, you'll see one of the main examples for today. And one of the main examples for today is can I graph exponentials, and then can I also use those graphs of exponentials to talk about logarithms. So here you have graph y equals 2 to the x, which is exactly the graph that I have here. How did I get to this graph? It's actually not that hard to do. So if you want, I can put it over here. So let's say we make a small table. And with this table, we'll call it f and or x and f of x. So then I chose negative 1, I chose 0, I chose 1, 2, and 3 for x. And if I took those and plugged them into the function, which we're calling this y equals 2 to the x, then I know that 2 to the negative first is going to be a half. I know that 2 to the 0 is going to be 1. 2 to the first is going to be 2. 2 to the second is going to be 4. And 2 to the third is going to be 8. So I took these points, negative 1 half, 0, 1, 1, 2, 2, 4, 3, 8, and I graphed them onto the graph here. So what will be the inverse? Well, I know the inverse just has to be flip-flopping the x and y coordinates. So instead of graphing negative 1 and a half, I would graph a half and negative 1. So if I do this in purple, so if I go a half and then negative 1, I'll be here. Instead of 0, 1, I'll go 1, 0. So 1, 0 will be here. Instead of 1, 2, I will go 2, 1, which will be right here. Instead of 2, 4, let's go 4, 2. And instead of 3, 8, let's go 8 and then 3. So now if I graph this, I think the sketch that I'll start to look at will be something like this. All right, that's not half bad. So here's my inverse, which I'll use my notation. I can say this is f negative 1 of x. And just like the examples that we saw above, we know that this is going to be reflexive around line y equals x. So then that hasn't changed. If I drop that in there, I will actually see that they are inverses of each other. If I took this original function that I had and I flipped it over the line y equals x here in pink, then I would get this one in purple and vice versa. But now the question becomes, is what is this inverse function? What is it actually going to be? What is its equation? So if I go back over here to where it says y equals 2 to the x and y equals log base 2 of x, I can actually find that out. So let's say that I started with y equals 2 to the x. I know the first step for finding an inverse is to switch the x and y. So then x would be equal 2 to the y. But then how do I bring y down? How do I solve for it? Well, the only thing that can bring down exponents in algebra is logs. So what I can do is take a log base 2 of both sides. So I can take a log base 2 of this side, and I can take a log base 2 of this side. Now, why would it be a good idea to take a log base 2? Like we said, it's something that can bring down an exponent. So now this y that's up in the exponent inside the log can become the coefficient. I'll have log base 2 of x equal to y times log base 2 of 2. What is log base 2 of 2? Well, if you remember what logs are, they're just exponents. What exponent would you need for 2 to get it to 2? That's just 1. So log base 2 of 2 is 1. Y times 1 is just y. So I'm left with y equals log base 2 of x. I did solve for y. That means the inverse is going to be log base 2 of x. So then if I was doing it this way, if I started with the original exponential, it would get me to the logarithmic as its inverse. But we do know that inverses should undo each other, so I should be able to start with the other one as well. So what about instead of starting with y equals 2 to the x, what if I started with y equals log base 2 of x? Well, the first step here would be to switch the x's and y's. So then x would be equal to log base 2 of y. How could I solve for y? Well, then I could just switch this to exponential form. I know that the base to this power should always be equal to this. So then y would be equal to 2 to the x power. Well, I just solved for y. That means that that's the inverse. So that would be the inverse is equal to 2 to the x. So even then, if I started with the logarithmic function and I found its inverse, I would get the inverse to be 2 to the x, which means that these two are actually inverses of each other. So if one of our big ideas here is going to be stating the inverse of an exponential or logarithmic function, we should be able to do it. It's actually pretty simple without showing a lot of the algebra. If I have 2 to the x as a function, then I know its inverse is going to be log base 2 of x. If I have anything else in terms of a number here in the base, then I know that the inverse is going to be log with that same base of x. So if I had 5 to the x, the inverse would be log base 5 of x. If I had pi to the x, it would be log base pi of x. And then the graphs will look very similar. So of course with graphing, we have to talk a little bit about domain and range. So how about really fast? How about just the domain and range of these two? What about the original function? So the original function f of x, what is its domain? Well, if you remember, the domain is all real numbers. We said that exponentials have domains of all real numbers. What is its range? It's from 0 to infinity, not including 0. So notice the graph does go up to positive infinity. What's the lowest that it goes? It goes above the x-axis. It doesn't quite get there. So it'll be from 0 to positive infinity. How about the inverse? Well, here in purple, I can say that it does look like the graph never goes to the left of the y-axis, so it does go positive infinity, it goes to the right forever, but the furthest that it goes to the left is going to be 0. It doesn't go to the left of the y-axis, and it doesn't touch the y-axis. What is the range for this function? Well, as it's moving to the right, it is moving up forever, so it goes to positive infinity. As you move to the left, it's going down forever, down to negative infinity. So if I was going to say the domain and the range for this guy, I can say the domain is all real numbers. How about the range? The range would be from 0 to positive infinity, not including either one. How about for the inverse function? We said the domain was going to be from 0 to positive infinity, and we said the range was going to be all real numbers. And if you notice something about this, the domain here was all real numbers in the original function, and the range was all real numbers here. The range was from 0 to infinity in the original function, and the domain was from 0 to positive infinity. And if you notice, they just flip-flopped. The domain here is the range here. And the range here is the domain here. And why is that? Well, domain deals with the x-coordinate, and the range deals with the y-coordinate. And didn't we have to switch the x and y coordinates in order to get from one to the other? So in that case, you're just switching x and y coordinates. The restrictions on x in the original functions are the restrictions on y in the inverse. And then the restrictions on the range in the original function are the restrictions on x, or in the domain of the inverse. So it's actually not that bad. So if you want to graph, my suggestion is always graph the exponential first. It's kind of harder to graph logarithms, but if I know the exponential graph, which is not hard to do, I can just plug things in for the exponent and the exponential. Then just switching the x and y coordinates will give me the graph of the log function. All right, guys, so there's the front page. So far, so good. If you have any questions, you can hop on over to the Google Hangouts and you can ask me some questions. I can definitely bring back up this piece of paper and answer any questions that you have about it. Okay, let's go to paper number 2. So we're almost done. There's not much more to do. That was the main idea. So now can I take 2 fresh graphs and can I talk about them? So of course, the easier place to start would be to start with the exponential. Hopefully you'd agree the exponential is this guy here on the left. If I was you, the first thing I would do is make a small table. So let's call it x, and let's call it f of x instead of y. That way we don't get confused, and we know for sure that that's going to be the original function, and this is going to be the inverse. So what would be some values that you should plug in? I think definitely plug in -1, definitely plug in 0, and how about 1 and 2? Notice if you go past 2, 3 to a higher power than 2 is probably not going to fit on this graph. So here we go. What if I take -1 and plug it in? Well, 3 to a -1. Remember, if you have 3 to a negative first power, then what that will do is it will flip the 3 over 1, and it will become a third. We know that 3 to the 0 power, anything to the 0 power is 1. 3 to the first is 3, and 3 squared is 9. So then if I graph these points that I have here, -1 and 1/3, will be somewhere right here, 0, 1, 1, 3, and 2, 9. So something like this. We do know that it's exponential. We know that all parent functions for exponentials have the x-axis as a horizontal asymptote. So I know that it will not touch or go past the x-axis, but I know that it will get infinitely close as we move to the left. So a graph for this function would look something like this. So really fast, can we talk about the domain and the range? Pause the video here and see if you can actually list out the domain, range, zeros, and the increasing and decreasing before I do. So pause the video and try it for yourself. All right, guys, so how about the domain? The domain is going, in this case, is going to be all real numbers from -infinity to positive infinity. And the domain for this is -infinity. To the left, it goes forever. To the right, as it's moving up, it's also going to go forever. So the domain will be all real numbers. The range is the y-coordinate. What's the lowest that this graph goes? The lowest that it goes is 0. We did say that 0 was a horizontal asymptote for all parent functions for exponentials. We know that the highest the graph is going to go is positive infinity, so we'll go positive infinity. We know we're not going to actually get to 0, so it's going to be a parenthesis. We know infinity is not an idea, not a quantifiable amount, so it also is going to get a parenthesis. Does the graph have any zeros? Well, what the heck are zeros? Zeros are x-intercepts. In this case, since the graph doesn't touch the x-axis, it can't have any zeros or x-intercepts. Therefore, we'll have none. So in this case, there are none. Is the graph increasing or decreasing? Well, just like you read a sentence from left to right, that's how you read a graph. So from left to right, it looks like the graph is going upwards. The y values are starting something really close to 0 and then growing up really quickly. So in this case, the graph is increasing. How about log base 3 of x? That would be the new part for today. Well, like we said, you shouldn't maybe just try to graph log base 3 of x right off the bat. Instead, use what you know about inverses. Since I know that these two things are inverses, we did say from the previous page that if I have log base 3 of x or 3 to the x, they'll be inverses of each other. If not, pause the video, try to find the inverses by switching the x's and the y's and solving for y. You will see that these two are inverses. So if that's the case, then I should be able to take these values from the table and construct my graph by just switching the x and y coordinates. So really fast, if you wanted to, you can say x and then you can say f negative 1 of x, so that would show the inverse notation. Instead of negative 1, 1/3, you can go 1/3, negative 1, instead of 0, 1, 1, 0, instead of 1, 3, 3, 1, instead of 2, 9, 9, 2. So let's graph. So 1/3, we know would be here, down to negative 1 would be right there. 1, 0, 3, 1, and then 9, 2. So it looks something like this. I forgot about my purple already. So let me break that purple back out. We know the graph will come downward like this. So it'll go forever in the negative direction. And then if I draw it out this way, try to draw a good sketch for you. Something like this. Okay, so I have this graph. I know that if I put in the line y equals x, then I could take this guy and I could flip it over just like we did in the other page. But you don't have to here if you don't want to. So really quick, pause the video. Let's talk domain and range and see where it goes. All right, so how about the domain? In this case, domain is the x-coordinate. Well, what's the farthest this graph is going to go to the left? It's going to go to 0, but it won't ever get to 0. Notice it never touches the y-axis or goes to the left of it. How far does the graph go to the right? It goes to positive infinity. We know that since we're not getting to 0 and we can't get to positive infinity, those are going to be open parentheses. How about the range? The range deals with the y-coordinate. So what is the lowest that the graph goes? It goes down to negative infinity. It goes down forever. What's the highest that it goes? Well, as it's moving to the right, it's also moving up. It's going to go up forever. So it goes from negative infinity to positive infinity, which is all real numbers. This is not a surprise to us. We saw from the previous page that the domain and ranges are just flip-flops. And that makes actually a lot of sense with inverses because we know inverses just change x's and y's. That's how you find inverses. So in this case, the domain for the original function becomes the range for the inverse. And the range for the original function becomes the domain for the inverse. In this case, are there any zeros? Well, this is going to be a little bit different than 3 to the x. We know 3 to the x never touched the x-axis, but does log base 3 of x hit the x-axis? It does. We can actually see that it hits one time at this 1, 0. So it does have zeros at 1, 0. Is the graph increasing or decreasing? Well, just like we read a sentence, let's go left to right. We'll start at this point, and then we can see that as we're moving to the right, the graph is going upwards. The y values are moving upwards, so in this case, it's also increasing. All right, guys, so in a nutshell, if we go back to the two ideas for learning targets, can you graph exponentials and log functions? Sure. Exponentials are not hard to do. Even if you don't know how it looks, you can make a little table and construct a graph. A lot of the parent functions do look very similar, depending on whether it's growth or decay. And the new part, graphing logs, well, if you know how the original function behaves, just switch or flip-flop the x's and the y's, and that will give you how the logarithmic function behaves. Okay, so if you have any questions, like I said, hop on over to the Google Hangout, and I'll be happy to help. Last thing that we need to talk about, transformations. So hopefully you didn't believe that transformations are done. I did tell you several times during class that transformations are not going anywhere. They're probably going to follow you around for the rest of your time in math. So just like we've talked about before, how do you move things right, left, up, down? How do you shrink them? How do you make them wider? How do you make them thinner? How do you flip them? Logs have all the same properties. So really fast, let's just go over some of the properties here. Parent functions are of the form y equals log base b of x, where b is greater than 0 and b cannot be equal to 1. B has to be greater than 0. We saw that was a property for logs. And then b can't be equal to 1 because if b was equal to 1, then it wouldn't be a logarithmic function. We know that if there's some a value in front of the log, that's going to control stretching. We do know from previous functions that we've seen before that if that a value is bigger than 1, then we're going to see a vertical stretch. If a is somewhere between 0 and 1, then we're going to see a shrink. which is going to make it wider. A stretch would make it thinner. We do know that if a is less than 0, so if it's negative, if there's a negative out front, then we know we're going to reflect over the x-axis. How about here? If I have a log base b of x minus h, I know that I'll be shifting right or left, and then we know k is going to be shifting up and down, just like we've seen before. Depending on what kind of numbers we see inside the parentheses, we know it kind of behaves opposite. So subtracting would move to the right, and adding would move to the left. We do know that k behaves like what you would think, so adding is going to move up, and subtracting is going to move down. So all the transformations together will look something like this, where we can say a is going to control thinner, wider, or reflection over x. We do know that depending on what h is, what values we see here, it's going to shift right and left. And then what the k values are going to shift up and down. So as an example here, we have log base 4 of x, which is this logarithmic function right here. Again, if you were going to graph it, I would start by graphing y equals 4 to the x as an exponential function and just switching the x's and the y's. And then what kind of a transformations do we see? Well, we don't see anything change with the a value up front. So that means that there's going to be standard size. There's no thinner, wider, or reflections over the x-axis. We do see a minus 3 inside of here. So in this case, every point is going to go right 3. So then you'd shift all the points right 3. It behaves opposite what you would think. And then plus 4 means go up 4. So remember, numbers on the outside of parentheses behave like what you would think. Plus is up and minus is down, where inside of parentheses, plus is to the left and minus is to the right. So how about really quick, can we talk about these parent functions and transformations? So then what would be the parent function for this y equals log base 2 of x minus 3 plus 4? Well, the parents, so maybe I can just write it one time here, so that way we can do it for each one. The parent in this case is just y equals log base 2 of x. How many transformations do you see? Maybe you should take a second to pause the video and see if you can answer these questions on your own before I just tell you the answers. So pause the video, try these, see what happens. If you get them wrong, no problem. You can erase, you can rewrite, and kind of go from there. Okay, pause the video and try it. All right, guys, let's see what you came up with. So in terms of transformations, I see 2 transformations here. So what will the first transformation do? I see a minus 3 inside the parentheses. So in this case, I could say it is going to shift the graph right by 3 units. How about the second one? I see a plus 4 on the outside. So this graph is going to shift up 4. And by that I mean a translation, right? A translation is a slide. So in this case, it will slide right 3 units and up 4 units. I don't see any a values changing. So that means it's going to be standard size, not thinner, not wider, and not flipping over the x-axis. So how about in B? What would be the parent function here? The parent function here would be y equals log base 2 of x. Notice I don't have anything changing inside of here. I don't have anything changing inside of here. The only difference is I have a 5 out front. So how many transformations do you see? I just see 1. So what is this transformation going to do? Well, I know this 5 is kind of like the a value that they're talking about. When we're multiplying by some number that's bigger than 1, we know the graph usually gets stretched out. In this case, it's going to be a vertical stretch. So we can say it like this, a vertical stretch by a factor of 5. Again, in this case, it's going to be a stretch. It's going to get thinner because this number is bigger than 1. If the number was less than 1, it would be getting wider. It would be a vertical shrink or a compression. All right, how about the last one? What would be the parent function for this guy? The parent function for this would be just y equals log of x, which in this case is a common log. What is the base for a common log? Do you remember? The base for a common log is 10. So I would see something like this. Now, how many transformations do I see? I see a negative out front. That would be my first transformation. I see a plus 4 inside the parentheses. That's my second transformation. And I see a minus 5 on the outside. This would be my third transformation. So in this case, what was my first transformation? This negative, it's going to reflect over the x-axis. All right. How about 2? If I add 4 on the inside of the parentheses, the graph will shift or slide left 4. And then last but not least, if I see a minus 5 on the outside of parentheses, then the graph will translate, shift, or slide down 5 units. All right, guys, and there we have it. So have we completed our 2 learning targets? Do you have an idea of how you can graph exponentials and logarithmic functions and say some things about their domain and range like we normally do? Can you also state the inverse of an exponential and a log function? And can you have an idea of what happens in terms of transformations? It's really not that bad. So if you have any questions, feel free to hop over to the Google Hangout. I can answer any questions you have. Otherwise, please try the assignment that I have back on Canvas, submit it, I can take a look at it, and we can kind of go from there. Hopefully you enjoyed the video. I do miss seeing you guys on a daily basis. It is going to be kind of tough for me not to see you for the next couple weeks, but hey, maybe if you come on over to the Google Hangout, I can chat with you a little bit and see how things are going. All right, guys, all the best. Let me know if you have any questions. Otherwise, I'll keep posting onto Canvas and trying to keep you guys going. I wish you good health, and I'll see you soon. Bye-bye.